Alright, we're just gonna wing it. Let's go ahead and start from the first slide. So what's up, guys? This is Giant Buff 3 here. A lot of people have been requesting for Banjo-Kazooie modding tutorials, and a commonality is they'll come into like the BK ROM hacking server, or even like the rando server, and they'll be like, "Hey, I want to help out, but I don't know how to code. Where do I start?" And a general, answer that they get is learn C, or learn hexadecimal and stuff like that. And then they are like, well, how do I do that? And it's like a bunch of tutorials online. And then like that's not wrong, but like it's not a very motivating answer. So this is my kind of solution, is I'm gonna try to go through the basics of like some coding aspects, some BK modding aspects. I'm not going to teach you how to code, but I will, for anyone who is actually interested and wants to kind of know which direction they should be going, kind of like, go towards it. So this is a very, very basic hexadecimal tutorial. I don't even cover like things like ASCII keys, or commands, or like MIPS or anything. It's literally just the basics of hexadecimal. So let's go ahead and begin. Do I click on the screen, or I guess I click on the screen? Okay, cool. So, how do we count normally? So, you would go like, 0, 1, 2, 3, 4, 5, 6. Actually, I didn't even start at 0, I started at 1, right? But like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then, after 9, you're like, hey, I don't have any numerical values. I'm gonna move a 1 to the tens place, and now repeat the process starting at 0. So you get 10, 11, 12, 13, 14, 15, 16, so on and so forth, right? So everyone here should know how to count. I'm gonna go ahead and move on from that. But the way we can kind of think about it is, for our regular counting system, like with 0, 9, and then 10, whatever, that is on a base 10. So what that means is that there are 10 values that you have before you add the next digit. So from 0 to 9, there's 10 numbers. So let's break down the number 372 as an example. So in the 10 to the power of 2's place, so the hundreds place, we have 3. 10 to the power of 1's place, so the tens place, we have 7. And 10 to the power of 0's place, we have a 2. And so, did the math down there, if you add 3, times the 100, plus 7 times the tens, plus 2 times the ones, you'll get 372. So, I think you guys can do basic math. Feel free to pause the video, and if you want to, like, just read what's on the thing and come back to what I'm saying. But I will kind of go a little faster than the slides are, because I do have a lot of text on the screen. So, what is binary? So for normal counting, we go from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we repeat with 10, right? Imagine instead of going all those 10 numbers, you just had 2 numbers. It is just 0 and 1. What happens after 1? Well, then you add a digit to the next place, so like the tens place in this case. It would be the 2's place. So, I think, hopefully you can see my mouse. So we have 0, 1, and it actually continues to go 2, 3, 4, 5, 6, 7, 8, 9, 10, but we are now reading it in binary. So it's 0, 1, binary 1, 0, binary 1, 1, binary 1, 0, 0, and so on. So just going to go over this slide a little longer than the last slides. We have one singular digit, right? And once we finish it off, we add it to the next one, bam. Then we continue, so it's 0, 1 again. And now this guy adds to here. This guy is like, oh, now I'm done, so it adds it to the next one, so it makes 1, 0, 0. And then we add 1 to here again. And then we add 1 to here again, but this is filled, so we add it to this next slot, which will make 110, like binary 1, 1, 0. And then we add to this guy again, and then once you add to this guy is 2, so it would add to this guy. This guy is now 2, it adds to this guy. This guy's now 2, it adds to this guy, and now we get a binary 1000. So hopefully that makes a bit of sense. I'm gonna go ahead and move on. So if we think of binary in powers of 2, we can still break down the numbers, right? So let's say we have binary 1, 0, 1. If I go back 2 slides, can I go back like this? Previous. So we had 10 to the power of 2, 10 to the power of 1, 10 to the power of 0. So I'm going to go ahead and go forward. Now we have 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0 for binary, right? So we have 1, 0, 1 as our number, right? And the formula is down there again, so it would be 1 times 2 to the power of 2, which in this case is not 100, it is 4. And then we have, the next digit, so it's 0 times 2 to the power of 1, which is 2. And it's not 10. And we add that. And then 1 times 2 to the power of 0, which would be 1. Still ones. And then we multiply that, and then we get this number would actually end up being 7 in decimal. I should write that on the screen, but it's fine. You guys get the point. Moving on. So that first way we were counting it from 0 to 10 is called decimal. And the counting from 0, 1, and then repeating the cycle is binary. You can kind of think of like dodecahedron, which is like a 10-sided die, I believe, or 10-sided shape. And then binary is like a bicycle where it has like 2 wheels. So how can we convert it from decimal to binary? Is there's actually a formula if we just use it from before with we keep going up on the scale for every digit. So this one's 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and we multiply it. So if our number is 1, 1, 1, 1, multiply this by 1, 1, 1, it's 1, 1, 1, 1, and then to the power of 3, to the power of 2, to the power of 1, to the power of 0. This one ends up being 8, this one ends up being 4, this one ends up being 2, this one ends up being 1. So all these combined equals 15 in decimal, which is our normal counting system. Now, it's easier to do it from binary to decimal because we are so used to just like, multiplying things in order to get like the decimal value in like regular math. The other way around is a bit different. So let's go ahead and go over an example. So let's say we have the decimal value of 10 and we want to convert that to binary. We now have to find the largest power of 2 that fits under the decimal 10. So 2 to the power of 0 is equal to 1. That is under 10. 2 to the power of 1 is 2. That is under 10. 2 to the power of 2 is 4. Still under power of 10. 2 to the power of 3 is 8. Still under 10. 2 to the power of 4 is 16. This number is too large. So we're going to go back 1. So this guy 8. And we're going to use this value. So it's 2 to the power of 3. We're going to remember that, by the way, 2 to the power of 3. But we're going to take this 10 and subtract what it would have ended up being. So it would have ended up being 8. If I go back 1 slide, previous, this guy is 8. And equals 2. So that's our remainder. So now we got to figure out the next largest power that fits into there. 2 to the power of 0 is 1. That's less than 2. 2 to the power of 1 is equal to 2. That's exactly what we need to finish this off. So now we have 2 to the power of 3 and 2 to the power of 1. So another way you can think about it is long division, right? So if you have 10, right? We'll take a large value, so power of 2, and we'll take 60 for example, right? It doesn't fit there, we'll move it over. 10, how many times can 8 go into 10? 1 time. So we're going to put that here, and we're going to subtract 8 from this value over here. Which, 10 minus 8 is 2. Now we're going to see if 4 enters. It does not, so we have a 0. How many times does 2 go into 2? 1 time, so we add a 1 here. Subtract 2. How many times does 1 go into 0? 0 times. So this would end up being what the binary value would be. 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, to the power of 0. We have 1, 0, 1, 0. so 10 in decimal is 1010 in binary. I hope that makes sense so far. Now, can we use other bases? Yeah, we can. So heads up, don't need to write this down. This one is just an example that is for your understanding. So there's no implication of this in Banjo-Kazooie or in I don't think any video game. So just hear me out. This is just for understanding for something later. So let's look at the power of 3. How do we count it? We would go from 0 to 2. So we go 0, 1, 2, and then we repeat the process. So it would be 1, 0, and then 1, 1, and then 1, 2. Now that we're done with this side, the next digit gets added over. 2, 0, 2, 1, 2, 2. Now that this guy is done, we move one over to here. That means this guy is done, we move over to here. 1, 0, 0, 1, 0, 1, 1, 0, 2, and then so on and so forth. Can we do it with a base of 8? Yeah, we can. And so 0, 1, 2, 3, 4, 5, 6, 7, 8. Once you get to 8, start it over. And then you go, 10. So just look at this one digit. 0, 1, 2, 3, 4, 5, 6, 7, 8. Once you get to 8, we add 1 to this next digit. So 2, 0, and then 2, 1, 2, 2, and 2, 3. So here's a little programmer joke for you guys. Why do programmers mix up Halloween and Christmas? Because oct of 31 is equal to dec of 25. The joke is that October's, shortened up version, abbreviation, I guess, is OCT, so it's like oct, like base 8. And decimal, which is, December shortened down, if you do the conversion rate between oct and dec, 31 is equal to 25. So this is probably more for people who actually used, base 8, which is not a lot of you. So moving on from this bad joke, we're gonna go to the next one. So here is why I went over base 3 and base 8 at all. Base 16. What is hexadecimal? If we go from 0 to 9 in decimal and 0 to 1 in binary, we don't have that many number values to go past 9. Hexadecimal goes from 0 to F. So hexadecimal is base 16, and after 9, we start to use letters of the alphabet. So let me go ahead and show you. So imagine a deck of playing cards, right? You go ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And sometimes you will say jack is the value of 11, queen is the value of 12, and king is the value of 13. You can expand this. Some regions have a joker, and joker can be like a wild card or 14. But it's as close as I can get, so I'm just going to use this base deck set. So ace through king. But so for the hexadecimal, imagine we replace the jack, queen, and king with A, B, C, D, E, and F. So we have 10, 11, 12, 13, 14, 15. So the numbers between 0 and 15 are all one singular digit. So I tried to align them as best I could. You can see that it starts at 0 and all the way goes all the way to F equals 15, which then we add the next digit over, which is 1 and 0. Now you know why I emphasized that so much in the earlier slides. But moving on. So in order to prevent the confusion between, is this a decimal number, is this a binary number, or is this a hexadecimal number, we are going to use notation. So for hex values, we're going to use 0x, and for binary, we're going to use 0b, and then for decimal, we're not going to have anything in front. So if I look at 1 0 in decimal, it is just 10, which is 10 in decimal. You guys are aware of that. Now if I have 1 0 in hex, we're going to show it as 0x10, which would end up being 16 in decimal. And if we have 1 0 in binary, we're going to say it's 0b10, which is 2 in decimal. Now, how do we convert from decimal to hexadecimal? Fun fact, if I go back a billion slides to here, it's the same formula, except instead of base 2, we are going to use base 16 for hexadecimal. So we're gonna take the value 1ab3. So remember, 1 is still just 1. A, however, is equal to 10. So we got to replace A with 10. B is equal to 11. And 3 is still 3. And then 16 to the power of 0 is 1. 16 to the power of 1 is 16. 16 to the power of 2 is 256. And 16 to the power of 3 is 4,096. Add them all together, it equals 6,835 in decimal. Now, if you want to do the reverse, it is the same as binary. You know how like this going from decimal to binary is the same kind of formula as decimal to hex? It's the same kind of reverse where you have to like do like the division. I don't have a slide for it. I don't have the time. I am moving on. So now, how do we convert from binary to hexadecimal? Well, there's two ways you can do it. You can either convert like the binary to decimal and the decimal to hexadecimal, you know, and then like vice versa. Or, and this is the cool part, if you memorize the values of 0 through 15 in binary, you can figure out any hexadecimal value. Hear me out. So, and this is gonna be a little confusing, so just bear with me. It'll make sense as I explain it out loud. So in binary, we use base 2, so it's to the power of x. Remember, it's to the power of 0, to the power of 1, to the power of 2, to the power of 3, etc., right? Hexadecimal uses base 16, so 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3. But 16 to the power of whatever can be broken down into 2 to the power of 4 to the power of whatever it was before. And for anyone who doesn't like math or doesn't remember the math, you can actually pull out this exponent to make it 2 to the power of 4x. Now, exponents, I don't want to deal with that. You're not going to have to deal with that. The key thing is this 4x can be grouped together. And by that, I mean we can use 4 binary values, or digits, I guess, to figure out a hexadecimal digit. So let's give an example. So in binary, we know that this is our version of 10, right? 1 0 1 0. And just to go over why this is 10, if we say this is the value of 1, there is 0 of them. Value of 2, there is 1 of them. Value of 4, there is 0. And value of 8, there is 1. So 8 plus 2 is 10. In hexadecimal, that would be A. So let's say you had the number 10101010. You can actually separate that into 2 different sections of 4, and it will look like this. One binary of 1010 and another binary of 1010, and you just mush them together in hex. So this guy looks like it's A, so we're just gonna put A in the front, and this guy looks like A, so we're gonna put A in the back. Ta-da! If you can split the binaries into groups of 4, and let me go back here. That's why this 4 is significant. If you can split them into groups of 4, you can easily convert any binary to hexadecimal and hexadecimal to binary. Ta-da! So these are all of the binary and hex values, like, translations that you actually need to memorize. Or you can do what I did back in here and just do the math for the binary as an example. Or however you want to do that. But if you memorize these 16, or just get a good feel of like the placements, like that's an 8, that's a 4, that's a 2, that's a 1, then you can easily convert between the two. And what's nice about binary is that anytime there's a flag in the game, right? So like you either have the flag or you don't, right? So like let's say you're in Banjo-Kazooie and you open up Mumbo's Mountain. You have either opened up Mumbo's Mountain or you have not. 0 and 1. Hexadecimal, however, can take a huge number. Let me actually go back a few things. Remember this number 1AB3? It can take a big number like 6,835 and shrink it up. So each of them have their uses. It really just depends on what you need them for. And I'm not going to go into deeper examples yet. This is just a basic tutorial, and I was just explaining why you would need, one or the other. But so moving on from there. Now let's get into number sizes. So let's think about digits, right? You know that the numbers between 0 and 9 are like the ones place. Between 10 and 99 is the tens place. 100 to 999 is the hundreds. 1,000 to 9,999 is the thousands. 1 million to 9,999,999 is millions. So those are kind of ranges, right? But you can technically fit a ones value in a tens slot. It would just be 0, 0. As well as you can fit a tens thing into hundreds, right? It would just be 0, 1, 0. Make sense so far? I hope so. Because in binary, there is a upper limit and lower limit. So for a bit, we can think of it kind of like our ones, where it is just a singular digit. And in this case, it's just 2. It's zeros and ones. For 4 bits, which we're going to call a nibble, it is between 0, which is going to be 0, 0, 0, 0, and 1, 1, 1, 1. As 0, 0, 0, 0 is the lowest number you can make with 4 digits, and 1, 1, 1, 1 is the highest number you can make with 4 digits. So if you thought nibble was a cute word, get ready for byte. A byte is 8 bits. And the lowest value it can be is 0, 0, 0, 0, wait, 0, 0, 0, 0, 0, 0, 0, 0. And the highest value it can be is 1, 1, 1, 1, 1, 1, 1, 1. So a byte is consistent of 8 bits, and half of a byte is a nibble. And then it starts to get unfunny. So if we have 16 bits, it's half a word. I wish they made something funnier, but it's like a chomp or something, but it's not. And then if we have 32 bits, it's a word. And you can keep going, you can get longer, but I'm gonna move on from here for now, because this next slide will actually explain why we don't typically go longer than 32 bits as a word. So now we're gonna look in terms of hexadecimal instead of binary. So if we have one singular digit, it's our nibble. So if I actually go back a slide, previous, this guy, these 4 bits, if you remember, this makes 15, or in our case, F. So a nibble is half a byte. And 2 digits, like, FF, would make a byte. And remember, this ranges from 00 to FF. It's not just, oh, it has to be like 10 or something like that. No, anywhere between 00 and FF is a byte. A half word is 2 bytes, so FFFF. A word is 4 bytes. And you'll more likely see words written in hex than you will in binary, just because of how big it gets in binary. So FF, 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 FF is a word, and I'm not gonna even say how many Fs there are, but all those 8 Fs, or all those 16 Fs, my bad, is a double word. So it's 8 bytes. and you will actually possibly see a quad word, which is twice as many F's as a double word, but I did not have space on the slide for that. But keep in mind that that is a thing that does exist. And you can get bigger. I'm not going to demonstrate that. So, now that we've talked about like the sizes of numbers, what kinds of numbers are there? So, there are signed numbers and unsigned numbers. So, basically, you can think of the absolute value, or you can think of positive and negative for now. Not exactly, but for now, you can kind of think about it that way. The next one is the size of the number, which is what we just went over. If it is signed. And then integers versus floats. So integers are kind of what we've gone over. Floats are what you would think of as like the typical decimal values, where it's like 1.36. The point makes it a decimal. But in order to prevent confusion, I won't use the word decimal anymore. I will use the term fraction or float whenever we get there. So, what are unsigned numbers? So, if I were to give you any number, right, this is where you would kind of think of it as the absolute value. This is always just the positive of that number. And now I'm saying don't take that with a grain of salt, because that's not the actual definition, but you can think of it as just the positive numbers. But signed does take into account whether it's positive or negative, and signed is actually the reason why I say you cannot use absolute value. And I'll explain that in the next slide. So let's say we have the number 1111, right? How do we know if this number is positive or negative? And spoiler alert, in case you're reading the screen because you watch anime, you weeb. But fun fact, we don't. We don't know if it's positive or negative. There's something that would tell us whether it is positive or negative, and I'm not going to get into that in this video, because this is not a C tutorial video. We will get to that later. But for now, let's just take the binary value 1111 and let's roll with it. So, if this number is unsigned, assume it's positive. So, we have 1111, which, if you remember from before, is equal to F. And F for us in hex is 15. And the other way, in case you just want to break it down, in case you want to practice this first one is 8. 8 plus 4 is 12. 12 plus 2 is 14. 14 plus 1 is 15. Now, with signed numbers, you actually have to separate out that first bit from the rest of the number. So, in 111's case, we actually have to take one singular bit from the front, and then every other bit is its own number. Now, that first bit you see, this lonely number, this guy determines if the number is positive or negative. If this value is 0, it is positive, and if this value is 1, it is negative. And if it's negative, we're gonna have to do like a little bit of math to figure out what the rest of this number is. So in order to, yeah, this is just explaining basically if we have the number 0111, we separate out the first bit from the rest of it. So that first bit is 0. We would know that this is a positive number, and we would just read 1111 as a positive number. So we would have 4 plus 2 plus 1, which is 7. Bam. Now let's go back to our old value, 1111, as a signed value. That first one's a 1, so we know it's negative. And the proper way to calculate what the rest of the number is would require bit flipping. But in order to simplify it, because calculators exist, we're just going to use a little bit of subtraction. We're going to take that value, so 1111, and we're going to add 1 bit to it. So it would be 1000. It's like one, I guess, binary place, 1-digit place, 1000, and we're gonna subtract this number. So, in this case, I refer it as the next highest bit. So, we're gonna round it up. So we're gonna have 10000 minus b binary 1111, which is equal to 1. Now we have this value, but we know it's negative, so we just add a negative sign in front of it, and now we have -1. Just as an example, if we have 1010 and we are trying to find out the negative version of it, because you see that first one's a 1, right? That first bit's a 1, so we move that aside, and then we have 010. We would still take this 10000, and we would subtract the 1010, and we would end up with 0101, which is -5, I believe. Someone can correct me in the comments, but I believe that's the case. So, do you see the difference between the signed and unsigned values? Now, if it's unsigned, we just take the value as is. If it is signed, we have to do all that math, where we separate the first bit and then have the rest of it. Make sense? I get that that's a little confusing. Feel free to go back in the video and review it to try to see if you understand it. You can also, if you're on Windows, I know that there's a calculator that can help you figure out like positive and negative numbers. It might use a lot of bytes, but just take the first, like, the last 4, depending on how big your value is, and you should be able to play around with it and figure it out. So floats, you love them, you hate them. So floats are those fractional numbers that we're talking about, like 3.14159265535. That's not even a lot of this is the pi. I don't know why I'm impressed by myself. But they're represented by 4 bytes every time. So if we have 1.0, you might think that 1 is just a integer, right? But the fact that we added a .0 to it makes it a float. So this guy would be represented as 3F8000000. 1.5 would be 3FC00000. That's that. And then even negative numbers can be represented as floats. Floats don't care whether you're positive or negative. The only thing that it has an issue with is rounding. So like the -420.69 isn't exactly this guy. In fact, actually, this is the closest it can get. And so I kind of like tried out a little, a few things. So it's close enough to the point where you can say it's that. But how do you calculate, how to get from this value to this value? I use an online calculator. I'm not doing the math. It gets complicated. It's not a good time. Just Google it. I use this one specifically, float.expose/. Just go to the tab that says, float. Actually, it should by default go on the float one. And then just plug in your hex value or plug in your decimal and you can figure it out. And the value can get huge and tiny. So, just play around with it. You'll figure it out. All right, so in order to see if you paid attention, I made my own little quiz show at the end. But this will also help you try to understand if you understood what happened in this video. So, what I'll do is I'll read the question out loud. I will read all the answer choices, and then I will give you 3 seconds to pause it before I say the answer. So, or maybe even 5 seconds. I don't know. We'll see how I feel. You've seen me use this notation, you twits. Which of the following represents bits? No, I'm not going to do the cringy voice, but... you've seen me use this notation, you twits. Which of the following is representing bits? So, in this case, we are looking for notation, not value, because technically these are all numbers. So, we have 1010, we have 0B1010, and we have 0x1010. I'm gonna give you 5 seconds. 5, 4, 3, 2, 1. the answer is B. That's representing bits. You can even see with a little B symbol on it, representing bits. The A is representing decimal, and C is representing hex. All right. Translate hex A0, but I hope you don't mind. What's the decimal value if the value is signed? I don't know. That's super cringy. So we have the hexadecimal value A0. Now, I want you to try to convert that to a decimal value if it were signed. Keep all of those specific details in mind. I'm not trying to rhyme. So I'll give you 5, 4, 3, 2, 1. So normally, if unsigned, A0 would be 160. And to make it negative, it doesn't just equal negative 160. It would equal negative 96. So the answer is B. I'm hoping that trips someone up. I don't know. Maybe. Whenever I took tests back in the day, I would be like, oh, 2 of the values say 160 and 2 of them say negative, so therefore it's got to be A. No, it's not A. It's B. So, yeah. Go ahead and plug in that math. Keep in mind that it is signed. If it were unsigned, again, it would be C. So, moving on. Does memorizing words give you a fright? Which of these values could be considered a byte? So, when I am saying considered a byte, actually, I'll go ahead and explain it after, but keep in mind, actually, no, I'm just going to count down and then I'll explain my reasoning afterwards. So this one might be a trick question, but I'm going to tell this full of tricks, so whatever. 5, 4, 3, 2, 1. In this case, the answer is A. Now, I know that it looks like a binary value because it is a binary value, but a byte does not care whether it's binary or decimal or hex. It is the range of values it can be. And in our case, a byte is 8 bits. And as you can see through A, it is under 8 bits. 420 is way too big to just be, to be a byte. And then FFFF is actually 2 bytes. So A would be the answer there. Converting these values is a pain in the butt. The number 3.14 would be a programming what? Now, I am looking for the terminology, not the definition. So, would it be fraction, decimal, or float? I'll give you 5 seconds. 5, 4, 3, 2, 1. It is a float. In the definition I used, it's a fraction. That's not what I was looking for, though. So, hopefully you guys picked float. And thanks for watching. I tried a little bit to rush through it. I feel like if you just wanted a PowerPoint, you could pause the video and read the slides, go over it. This is just supposed to be a very basic overview of what hexadecimal is. There are way better tutorials online, but hopefully this gives you a place to start. I'm not going to say the generic like, comment, subscribe for all of the videos, but this is a freshly made channel, hopefully to educate people. I'm not making any money out of this. I don't care to make money. I really just want the community to grow and to have a place to start in case you guys are trying to learn. Let me know your feedback down below. If I got anything wrong, call me out and I'll try to pin you. I'm not sure how many comments I can pin, but I will make like a correction video or something like that, or even like when we make the video. I don't care. I'll remake the whole video. As long as like we understand what's going on and stuff. If you have any ideas for what you would want in the future, let me know. And hopefully this helps someone out. Until next time, actually, I want to exit this way. Peace.